Well, hi guys. Today we're going to do two things. We're going to watch me do a description of the simple pendulum, and then Mr. Drood, who we thank for being here, is going to cue up, hopefully, a MIT lecture that I've got a link to for him that shows Professor Lewin at MIT doing an awesome presentation of the simple pendulum, and he's going to derive some things using calculus and differential equations. I'm going to avoid that using references to things we've already done, and I'll try not to be very cumbersome or verbose. Let me begin. All right, we're going to have a vertical line here from which we are going to move our pendulum, and we're going to move it up to here. All right, we have a mass on the end. It's got a length L and an angle theta. It's been displaced from its equilibrium, which might have been right about at that point. And you get the idea. It's going to swing back and forth. Now, if you'll allow me to remind you, earlier in the year we did a plane that had a right angle. We put an object on the plane, and we analyzed the components that were associated with it. We said that it had its mass down, or its weight directly down. It had a component, therefore, in and out based on that angle, which we proved was that angle. And it had a normal force going up that way. And we composed those vectors and said that that was mg sine theta, and going down was mg cosine theta. Right, the normal force was going up the plane, of course. And then we were in slanting world, and then whether or not there's friction is an entirely different issue. I would like to say that this situation, if the angle theta is very small, is analogous to this guy sliding down a plane. All right, he's going to have his weight going down, and if you'll allow me to extend that and extend this, I could convince you that theta was right there. Right there, you get a couple of parallel lines with a transversal crossing it, and any math teacher could explain that to you. I'm sure Mr. Bernstein did an outstanding job in geometry, convincing you that that relationship was true. But keeping in mind that it is true, I still have the same forces as slanting world. I got myself some mg going down. Therefore, in this direction, down the plane, right, analogous to the situation up in the upper right-hand corner, that force is mg sine theta. That is the restoring force, pulling the ball back into the left to where it came from, and then, of course, changing direction when it got to the other side. And moving this way, of course, is mg cosine theta. All right? And then the string is pulling up, and instead of a normal force, we have the tension going up that way, the force of tension. All right, but for our simple pendulum, which is a mass on the end of a string, and the string again is massless. If it a non-simple pendulum would be like a ruler that you grabbed at one end and let swing back and forth, where the mass was distributed along the entire length, as opposed to just being at the end right here. So this is how we begin our discussion. All right, so hopefully that is okay with you right there. I would like to then quickly move to a new slide, if that's all right. And I'd like to say that this, come here, circle, from a math class where this was the radius and this was theta, we called the arc that was subtended, this blue line right here, S, we called that the arc length. All right, some algebra 2 / pre-calculus, and we said the relationship that existed between these guys is S is equal to the radius times the angle theta. Very easy to convince you of that. And through some basic algebra, we'll just say that theta is equal to S over R. S over R. All right? Now this is theta has to be measured in radians. which we discussed what a radian was yesterday in class, and everyone was comfortable with that. So keep that in mind. Theta is equal to S over R. I'm going to come back to that relationship very soon. All right, now, new slide. All right. I'm also going to say that when we pull the pendulum to the side, it's a lot like when we did the spring motion, an object moving from an extended position back to equilibrium to an extended position, where the minimum and maximum positive and negative positions were called the amplitude. We defined the position at that time when it was displaced to the right or left, depending, as cosine omega t. We did that based on the old sinusoidal equation, y equals a sine bx plus c plus d from math classes, getting rid of the c and d, saying we don't need that, and then saying that the vertical axis might as well be a horizontal axis depending on our frame of reference, which we're very comfortable with. We took the derivative of that, which if you're a non-calculus person is not critical, but we said you could just easily memorize the equation, and that's a omega sine omega t, chain ruling it up a little bit. Should have a negative sign. Don't get mad at me, Marshall. I know you were about to chime in there. And x double primed v primed is acceleration, and that is a omega squared, a omega squared cosine omega t. When I say whoops, I'm accidentally hitting buttons that pop things up saying save, export. All right, so look, all we did there is basically say what the equations were from our previous lesson on springs. But since the motion of the pendulum is, as shown, similar to the spring, any force of the restoring force, that its position can be described with these, position, velocity, and acceleration can be described with this family of equations. So now we have 3 slides with relationships that we are going to now use. We're also going to tie that with, yesterday we said that the small angle approximation, that the sine of theta for angles that were small, measured in radians, is equal to theta. That's if we plugged into our calculator units, and yesterday we actually did the sine of 5 degrees. We converted 5 degrees inside by doing this, and showed that whatever values we got, that value right there, the sine of that, was actually equal to that. It was really, really close to within like a thousandth of a decimal. The flip side of that is, for small angles, the cosine of theta is approximately equal to 1. And if we did that same one, the cosine of 5 degrees converted to radians, it would come out to be like 0.998 or some number like that. So these are 2 approximations that we need to use for what I'd like to do. All right, now I think we have enough tools to go back to our lecture, all right, on the simple pendulum with our goal. Let's get to what the period is. All right, you ready? All right. New slide. All right, new slide. So keeping in mind our picture here, draw a little smaller, all right, with theta there, and I'm going to call this distance S, all right? That's that arc length, and if you recall, S equals R theta, so so at the moment, now S equals L theta, or theta equals S over L, again from that previous slide. All right, and with our idea that Newton's second law would let me write something like F net equals ma, the net force, the only force acting in that direction at the moment in our slanty world analogy is, all right, so now I've got my g theta from the previous slide is equal to a omega squared. Now here comes our excitement. Remember, we said that theta on the previous page is equal to S over L, and I'm going to then say that the A, if I could just draw this, give me my pen, right, the amplitude of our motion, right, and the amplitude of our motion is how far we move from equilibrium. We're going to say that that's the amplitude over to there. But that amplitude measured in almost a straight line is just our distance s. So I'm going to go up here and say g theta is really the same as s omega squared. Again, I'm going to say that the amplitude is s for our motion. And I'm again saying that for a small angle, it's almost like this guy is moving in a straight line going down. Alright? So I've got g theta equals s omega squared, and I'm going to replace theta on this other side with s over L. Alright? So I'm using the approximation up here in the right-hand corner and putting that in there. Alright, well, the s's are both on the top things, right there and there, right? And now I've got, if I'm just going to rewrite it, omega squared is equal to g over L. Getting ready for our final blow, I'm going to take that guy to the next slide. Omega squared equals g over L. Omega squared equals g over L. I forgot if I wrote a script L or not. Now, back to our sinusoid in the old y equals a sine bx world without that other stuff. Alright, we always said that the period is equal to 2 pi over b, right out of pre-calc. Alright, so in terms of our equation, where we had x equals a cosine of omega t, right? Playing the role of b is omega. So period, is equal to 2 pi over omega. This is a common physics formula. All right? I don't want to digress, but that's the same as saying period equals 1 over frequency, and that frequency, or omega rather, equals 2 pi f. Right? This is a common occurrence in the old physics community. All right? But we'll use those guys a little bit more later. So t equals 2 pi over omega, and now I probably didn't leave myself enough room. I'm going to take this concept right here, and the t equals 2 pi over omega, and I'm going to take the omega, and I'm going to, where's my laser? I'm going to take that guy. Oh wow, it had a sound effect. And I'm gonna do it again. Wow, I had the volume down before. Now I can really hear that. I'm gonna put omega in here. But what is our omega equal? Well, our omega is equal to the square root of g over L. So now subbing in right there, I'm going to get t is equal to 2 pi over the square root of g over L. I'm going to go to a new slide really, really quick. T equals 2 pi over the square root of g over L. Alright, well, in keep, change, flip world, this is just going to be 2 pi times the square root of L over g. Alright? Take a look at that. That is the period of our simple harmonic motion, and our oscillator here is the pendulum. All right. In your experiments tomorrow, you'll notice how this equation bears out with your experimental results in your tasks. All right. Now, that's the end of this video. I hope it wasn't too long and painful. I would have done a better job in class. Now, Mr. Drew will hopefully queue up the other video right now, and you can see, Professor Lewin, to me, he has Mr. Brower's good looks, and maybe a little bit of my personality. The guy's a stud. All right, I'll talk to you soon. Next video, Mr. Drew, please.